Helicopters are some of the most versatile aircraft going around, but they're also some of the most challenging aircraft to design. In this podcast, we're going to be looking at the aerodynamics of a helicopter's rotor, and then how that changes with forward speed. It might not seem like a big idea. Forward speed versus hovering or even flying forward at different speeds, the rotor is still producing thrust, so why should it change? Well, there are a few reasons why it might change. The first is that wakes from each blade on the rotor might interact with each trailing blade a little differently. And then there is also the fact that the faster you fly forward, the greater the velocity of the blade rotating forward will be. The blade that is then rotating backwards will also see a different local flow. And to give you an idea of what I mean, so in figure 1, if we scroll up a little bit, on the right here, we see a cross-sectional cut through a blade, and you can see that it is very airfoil shaped. Now, the angle shown here, the theta, which is the angle of attack, is really one of the major things to think about here, because first of all, if you have a wake from a blade upstream hitting this blade, then that theta angle isn't going to be what you think it is. So you might think here it's 5 degrees, but depending on what the flow is doing, it might be 4 degrees or 10 degrees or whatever. So if you have that wake hitting the flow, that means that the wake, hitting this blade here, the actual flow hitting it won't be the same as the free stream flow. It might be, it probably won't be, and it'll probably be a little bit slower, and it'll almost certainly be at a different angle, and it'll also probably change from the span to the tip. So depending on where you are on this trailing blade, the wake you see will be different too. It'll probably be more chaotic. Another reason why this angle theta might change is because on helicopters, it is very common to have the blades actually pitch a little bit around the center plate as it rotates its 360-degree revolution. So that means that the blade going forward will be at a different angle of attack to the free stream flow compared to the blade that's retreating. The main reason for that is it helps equalize the amount of lift each blade is producing. It's a little tricky to conceptualize, so let's break it down here. So in figure 1, on the right again, we have this blade rotating forward, let's say. So it's rotating into the free stream flow. As such, the velocity the blade actually sees is the oncoming flow plus the velocity rotating forward. That velocity is a function of the rotational speed, the angular velocity, and the distance away from the center. So a section of the blade that is 1 meter from the center will have a translational velocity half that than a section of the blade that is 2 meters away from the center. So in reality, as you go along the length of the blade, the speed that each blade section is seeing changes. Now, when you sweep the blade back around, the velocity is different again. You have the free stream flow speed and more likely the wake speed that you're seeing, but instead of adding that velocity to the blade that's rotating into the flow, it's now rotating away from the flow. As such, you have to minus that blade's velocity from the surrounding flow's velocity. Now, as the forward flight speed increases, that difference becomes more and more of a factor, and to illustrate why that is, let's consider the helicopter in just hovering. So it's not moving forward or backwards or side to side or anything, it's just hovering. So the speed, not the velocity, but the speed of the blade rotating forwards is the same as the speed of the blade rotating backwards. That's because there is no free stream flow adding or subtracting additional speed to the blade. In this configuration, the blade rotating forward will produce the same amount of lift as the blade rotating backwards. And that is the general description of what is happening in hover. So when you start to increase the forward velocity now, you have this free stream flow component which changes the blade's velocity relative to the flow it is seeing. And that is really the important part thing here, the relative velocity, because we don't actually care what the velocity of each blade is compared to the ground, because that doesn't matter to its aerodynamics. What matters is what the relative velocity is to the flow hitting it. And that is why I also clarified earlier about the wake interacting with the blade, because the more that wake's velocity differs to the free stream flow, the more different the blade's performance will be compared to what we expect it to be. And I covered that idea in a video on our YouTube channel called why the effective angle of attack is so important, Aero Fundamentals number 63. And that is really the crux of today's podcast, how forward speed affects each blade's performance. And to find out what occurs, we're looking at this paper called, if I scroll up here, modeling the helicopter rotor aerodynamics at forward flight with free wake model and URANS method. So it's open access, and you can find the link below, and the DOI is at the top right here. So the title is a little complicated. I'll explain what it means. What the authors are doing is simulating the aerodynamics of a helicopter's rotor at different forward speeds with two different methods. The first is the free wake method and the second is the URANS method. So these are two different numerical approaches. The free wake method is quite simple, which models the vortices coming off an airfoil or rotor, and it can't do turbulence or boundary layers because it only looks at the circulation and vortices created. So it isn't as accurate as something like a Navier-Stokes solver, but it is more accurate than a simpler approach like the basic lifting line theory, which doesn't model wakes. So the major benefit of the free wake method is that it is very quick, and there is also another very similar approach, and that is called the fixed wake method. So the difference between the fixed wake approach and the free wake approach is that for the fixed wake approach, as you might expect, the wake coming off the blades don't evolve over time. So if you have a vortex coming off of it, it just sheds downstream and will always remain intact and at the angle that it was shed from. The different parts of the wake won't interact with each other and induce any velocities or anything like that. The free wake method allows the wakes of each blade to interact with each other, and that will typically yield more accurate results because the wake can now deform as it should do. Now, for the URANS approach, which you probably have heard of, it stands for Unsteady Reynolds Average Navier-Stokes, which means that it doesn't solve any of the turbulence directly, but rather it uses something called Reynolds stresses, and then you can choose how to solve those. In that way, you approximate the turbulence. And this approach is typically much more accurate than the free wake method, and usually more accurate than any method that doesn't account for viscosity in the flow, but it is really an entry level to Navier-Stokes CFD. The only approach lower than this is the RANS method, which is steady state. So the URANS method has its benefits. It's then the more advanced Navier-Stokes approaches. It's much faster, so it can be good if you need to simulate a bunch of different things or a very complicated thing. So what the authors are actually doing in this paper is simulating the rotor at different forward speeds with these two different approaches to see how good the free wake method really is, and whether you can use that instead of the URANS method case because it's even faster, maybe like 100 times faster or so. Non-viscous solvers are way faster, but that comes with a penalty in terms of the accuracy. Let's now move to their setup. So in figure 2, we see their geometry, and the blades have a rectangular planform on this top left figure. Now, because it has a rectangular planform, there's no taper. That means that we should be getting strong tip vortices, and we'll see later if that is the case. Now the profile is a NACA 0012, which means that it's symmetrical and has a maximum thickness to chord ratio of 12%. And that alone means that if you didn't pitch the blades, then you wouldn't be producing any lift or thrust. So the authors pitched them to 8 degrees, which is a fairly moderate angle of attack for a NACA 0012. It's well below the stall angle of attack. They also had 4 blades, each with a span of 1.2 meters and a chord of 0.15. So that means that you have an aspect ratio of 8, which is pretty good. That should reduce some of the the blade tip vortices a little bit, but still there should be some. They then tested this setup at an advanced ratio of 0.05, 0.1, 0.15, 0.25, 0.35, and 0.45. So what the advanced ratio is, which is denoted by the Greek letter mu, is a ratio of the forward speed of the helicopter to the speed of the blades turning. That means that when you have an advanced ratio of 0, it means that the helicopter is hovering because it isn't moving forwards or backwards, but the blades are still rotating. An advanced ratio of 1 means that the helicopter is moving forwards at the same speed that the blades are turning. So here they're testing up to from 0.05 up to 0.45, and 0.45 is still pretty fast. So for their URANS setup, they used ANSYS Fluent, which is a top-tier CFD software, but also very expensive. If you want to learn a completely free top-tier CFD software, then check out our courses on OpenFOAM here. Now, they also used the Spallett-Almaras turbulence model, which I think is okay here, mainly because the flow hitting the blades will be so turbulent. I mean, you have wakes from other blades hitting them. That's a very turbulent flow, so the Spallett-Almaras should be okay here, I guess. One thing I'm not too sure about, though, is whether they used compressible equations or not. They say in the last paragraph on the right here, something about compressibility, but I'm not sure if they actually used it or not. And ideally, I think compressible flow would be good because the blade tips have a translational speed of 45 meters per second. That puts them at around Mach 0.14. And that value is well below the Mach 0.3 rule of thumb when you should be using compressible equations. But in another video on our YouTube channel called When is Air Compressible? Aero Fundamentals number 48, we go through the equations governing the density of air and how it is affected by the Mach number. Now in that video, we showed that at around Mach 0.3, the error in the density is actually already a few percent. So perhaps the rule of thumb here of Mach 0.3 is when you should be using compressible equations should be lower. Anyway, here I'm not too sure if they used compressible or not. Let's now move to figure 2 where we see their mesh, and you can see that it's unstructured. The cells are of all different orientations and sizes. And this is highly indicative of the authors expecting a very chaotic flow around the blades. And that makes a lot of sense considering that the weights from other blades are now going to be hitting each blade. So the flow is going to be very jumbled up. So an unstructured mesh is good here. And the key difference between a mesh here for these blades compared to an airfoil mesh just by itself is that in the airfoil case, you'd probably use a structured mesh because you know that the flow is going to be well behaved mostly over it. So you can go with a structured mesh approach and save some cells. Here, because the wake is, or the flow hitting it is awake effectively, you don't really know what the flow is going to be doing, so you need to have a more unstructured mesh to get a more accurate result. That means that you have more cells as well. So one impressive thing that they had here was that they used the Y plus value of 1 or lower over their blade surface. And that is impressive because when a lot of people use the Spalart-Almaraz turbulence model, they often go to higher Y plus values because it can handle these higher values. But if you go around 1, then it's usually a bit more accurate. So the authors didn't skimp here on the cells. And for those interested in how long it took to run one of these simulations, they say that on 150 cores, it took 160 hours, which is quite a lot. So some things that are missing from here is that there's no mesh independence test. In fact, I can't find how many cells they even used either. Based on their solving time, if I were to hazard a guess, maybe around 50 million cells, I'm not too sure, but it would be quite high. And something that is really good is that they simulated all 4 blades. They didn't just do like 1 or 2 and then use boundary conditions to approximate the other blades. So that approach, if they did that, would have saved some cells, but it would be dramatically less accurate. So they did a good job here using all 4 cells and really going with a lot of cells. So there's nothing about the mesh independence study though. There's also only one validation section, which we can see in figure 6 if I scroll down. So in figure 6, let me zoom in a little bit so we can see a bit better. So these plots here, we can see the experimental data plotted in the black dots while the simulations are in the blue and red lines. I'm not going to go through what these values are right now because we'll cover that a little later. All that's really important right now is that the simulations agree pretty well with the experimental data. So you can see that the black dots here are lining up pretty well with the other lines. The exact values are off, but the general trends are definitely there. So as such, I think that we should look just at the results as general trends and not like accuracy within 1% or 2%. It's more like around maybe 5, 10, 15, 20%. And speaking of the results, let's now move to the results. So the first parameters that the research looked at were the thrust and power coefficients. We can see the results in figure 4. So the thrust coefficient is the amount of thrust produced divided by the dynamic pressure at the blade tips multiplied by the rotor area. So when you think about it, it's effectively the thrust divided by the kinetic energy of the flow at the tips per meter. The authors also use the power coefficient, which is very similar to the thrust coefficient, and actually it's related in that it's equal to the thrust coefficient to the power of 1.5, then divided by 2. So in figure 4, you can see that the relationship between these two quantities of the rotor is quite obvious, like it's about to the 1.5 power. And what that tells us is that there's a fairly linear trend between the thrust coefficient and the power coefficient. It's obviously to the power of 1.5, but as you go to higher power coefficients, the line flattens out, becomes quite linear. That's pretty good in terms of if you know what the power coefficient is, you can get a general idea as to what the thrust coefficient should be too. And that also means that at lower power levels, the amount of thrust you get is relatively high. Then at higher power levels, the amount of thrust you get by increasing the power coefficient doesn't really increase that quickly. And there should probably be some of a plateau going on as you go to higher levels. As a side note, both the URANS and free wake methods give more or less the same result here. So this relationship seems to be quite good. Now in figure 5, we see the wakes of the blades at different advance ratios. This is quite interesting. So in the top left, we see the lowest advance ratio, which is 0.05, which means 5%. The helicopter is going forward at 5% of the blade rotational speed. And that's pretty close to hover. Now the blue wake, I'll zoom in a little bit here so we can see a bit better. Too much, there we go. Okay, so the blue wake is the wake from the CFD, while the lines are the actual vortex filaments from the free wake method. The results are pretty similar, but the URANS shows that the wake doesn't push down that much. It flattens out and flows backwards more. This is actually an interesting point because if the wake gets squished more, it will likely affect the blades more because it can't flow away from them as quickly. It kind of just sticks around and messes up the rest of the blades. Now, as the advance ratio increases, if I zoom out a bit and look at the other plots, here we go. So as the advance ratio increases, so from left to right, top to bottom, the wake gets squished more and more and the flow moves more horizontally than vertically. What that suggests is that the advance ratio increases, the wake from each blade is going to affect the neighboring blades more. One thing I'm not too sure about is the tilt of the rotor though, because at higher advance ratios, the rotor should be tilted forward a little bit more. And we've all seen this in helicopters as it pitches forwards to go faster. It's now going at like an angle instead of being horizontal. I can't see this pitching happening here, but maybe there was a reason for that. Now, in that case, if the rotor tilts forwards more, you'd expect that as the forward speed increases, the wake should be jettisoned downwards, relatively speaking, more and away from the rest of the blades. These plots don't show that, so there might be an inaccuracy there. Anyway, these plots also show the top views. So in each plot, you can see that there's these blue circles from above. And one thing to note is that for each one of these plots, there's major wakes from the blade tips. Those are undoubtedly tip vortices. So looking from this view, it seems like those tip vortices are the main wakes that are then impacting the rest of the blades. If it weren't for them, the wake would be pretty minimal and probably each blade would be performing a lot better. So that's probably why so many helicopters have very sharp taper at the blade tips, and also why we saw from a couple of weeks ago in a podcast called How Engineers Optimized These Helicopter Blades, podcast 232. We saw that sweeping the tips gave a lot better results than unsweeping them. It's probably for that reason. Sweeping the tips results in slightly lower, weaker tip vortices, smaller wakes, and better performance. Anyway, in figure 6, we see something called the CN distribution. So down here, there's quite a lot of graphs here. I'm going to try to do my best to show them all. So CN means the normal force coefficient, and this shouldn't be confused with lift or thrust because this is actually the normal force to the blade's chord. And because these blades are pitched to 8 degrees, the normal force is slightly skewed. Most of the normal force will be in the lift direction, but it won't be a little bit. So these graphs are close to the lift produced as you go to the root. That corresponds to 0 on the x-axis, and the blade tip is 1 on the x-axis. And the advance ratios here are shown too, so 0.05 all the way up to 0.45. Now you might have noticed that for each advance ratio we have 4 different graphs. Each graph corresponds to a different psi value, 0, 90, 180, and 270 degrees. 0 degrees is for the blade going straight back, so the back blade. 90 degrees is the right blade. 180 degrees is the front blade, so the blade pointing forwards. And 270 degrees is the blade pointing left, so the left blade. Let's first concentrate on an advance ratio of 0.05, so this top left part here. I'm going to scroll over a little bit so we can see them all. Maybe need to zoom out a bit. Okay, that's better. So the blades that are actually producing the most lift here are the blade tips for 90 degrees and 180 degrees, so the right and front blades. That's a little surprising from this point of view because the right blade is moving faster compared to the free stream flow, so you might expect it to produce a greater normal force. And that's considering that I'm pretty sure this coefficient is normalized to the free stream velocity, so if you have a faster speed, you're kind of like cheating the equation and getting more energy even though you're still rotating at the same speed. You have the additional kinetic energy from the flow hitting it from upstream. But anyway, even though this psi value of 90 has higher normal force production. The psi value of 180 also has quite high normal force as well. So they're kind of balancing out. And I think the reason why is because the front blade, even though it doesn't have a faster relative velocity, it's not seeing a wake from any of the other three blades. On the other hand, the right blade is getting some of the wake, so its performance is greatly reducing. As the advance ratio increases though, this trend doesn't hold because the right blade, which is moving into the free stream flow, produces more and more normal force as you go down these graphs. And that makes a lot more sense because despite being in a wake, it's seeing like 10%, 20%, or even 45% faster flow approximately. And that advantage is hard to beat. You have so much more energy now. And so even if the front blade is throwing a wake into that right blade, the additional velocity just overrides that wake deficit. So you're producing more upwards force, which is mostly lift. So the general trend here is that increasing the forward speed makes the blade that sweeps into the flow produce more normal force. And reducing the speed results in the right and front blades becoming pretty equal because the additional velocity you have starts to equal out with the wake deficit that you're getting on the right blade. So these two front and right blades are now equaling each other in terms of their performance. What about the other two blades though? What about the left and back ones? So that's the left one is 270 degrees and the back one is 0 degrees. At the lowest advance ratio, so 0.05, the top left plots the back one is really performing a lot worse. So that makes a lot of sense because it's probably copying all of the wake. The left one is performing slightly worse than the right one and front blades. And that makes sense because it too is at a slight velocity deficit and also seeing a wake. So it has a wake deficit and a velocity deficit piling up. Now, as the advance ratio increases, the back blade stays pretty steady in terms of its normal force coefficient, but the left blade really drops like a rock. I mean, literally at an advance ratio of 0.45 to the bottom right plot, the 270 degree plot shows that it's struggling to produce anything. Like literally it's just falling off. So the general trend here is that there are two major effects affecting the blade's performance. The first is the wake hitting them. The second is the free stream velocity, the advance ratio. The more wake the blade sees, the worse its performance. As such, the front blade has a natural advantage. But the faster the free stream flow is, the better the right blade is, so that blade sweeping into the flow performs better. And this effect is far more dominant than the wake effect, so at faster advance ratios, it overrides everything and makes whichever blade is sweeping into the flow perform way better. Now there is one more set of data in figure 7, but it's a little confusing, so let's go through it and explain what they mean. So overall, the data plotted here is for the vertical velocity. The x-axis is the z on r location, in other words, how far to the left or right you are. -1 means that you're at the tip of the left blade, 1 means that you're at the tip of the right blade, and 0 means you're in the middle of the rotor. The y-axis is the vertical velocity in meters per second. Now the top two graphs, so the top row are for vertical locations, x on r is 0, in other words, in line with the rotor disk. The y on r location is -0.05 and -0.25, respectively. What that means is that the left graph is 5% of the span backwards, while the right graph is 25% of the span backwards. What these graphs show is that for hover mode, so advanced ratios of 0, the vertical velocity distribution is symmetrical about the rotor. So the blades are performing symmetrically as you might expect because no blade is sweeping into the flow or away from the flow because there is no free stream flow. And then each blade is seeing the exact same wake because effectively the wake isn't being skewed or taken away by the free stream flow. So as expected, the closer you get to the tip, the greater the vertical velocity is. In other words, the closer you go to the tip, more lift is produced. And that is purely a function of a faster relative velocity. Now the next three rows are for advanced ratios of 0.05, 0.15, and 0.05 all the way to 0.45. As expected, as the advanced ratio increases, the graphs become more and more asymmetric. It's a little hard to tell just from these graphs which blade is doing better, the left one or the right one. The left one corresponds to the left half of the graph, and the right graph, half of it corresponds to the right blade. But one possible telltale sign is that If you look at the tips, so -1 and 1 on the x-axis, as the advance ratio increases, the speed here becomes more and more positive for the right blade. What that means is that I'm pretty sure these positive values are corresponding to the tip vortices. So the tip vortices are now like washing flow upwards. That's why we get this positive velocity. If that's true, then it's very likely that the right blade is producing more lift, at the very least at the tip, because the tip vortices are stronger. Now, as for the bumpy values going from the root to the tip, that is likely from the blades impacting the wakes. So those wakes are affecting how much lift is produced at each section now. And with that, we come to this podcast. It was quite interesting to see how the greater the advance ratio is, the more the advantage overrides the wake's negative effects. And the right blade, the one that's going into the flow, produces more and more normal force, while the left blade, which is going away from the flow, produces less and less normal force. But then at lower advance ratios, the front blade is pretty equal to the right blade. So if you like this podcast, hit the liking and subscribe buttons. And if you want to learn a free and top tier safety software off OpenFOAM, then check out our courses below. And if you're staying on YouTube, YouTube thinks you will like this video, so check it out. Peace out, amigos.